Okay, so let's talk about fits. As you may know, fits are very important when we deal with assemblies. Fits define how tight or loose an assembly feels. Ready? Let's do this. As you may already know, when we have components assembling into one another, fit will be a key factor in defining the tolerances for each component. Fit defines how much clearance there is between two components. This clearance can also turn out to be negative in cases where force is required for assembly, but let's not get too much ahead of ourselves. Let's start with what the main types of fit are. We have clearance fit, interference fit, and transition fit. Imagine having a shaft and hull that are about to be assembled into one another. These two features have the exact same nominal size of say 20 millimeters in diameter. Now, by using different tolerance combinations next to the nominal size dimension for the shaft and the hull, you get to have different levels of fit. You can have very loose fits when there is larger gap between the two, and you can have tighter fits when the gap is smaller or even non-existent. When you have your tolerances for both the shaft and the hull in a way that you always get a gap between the two features along the entirety of their tolerance zones, you have a clearance fit. Clearance fits are used when you need free movement and ease of assembly between your features. This also means your features get to disassemble easily, so you need to use this fit when functionally allowed. Also remember, you cannot get very high precision in alignment with clearance fits in general due to the fact that there is always a clearance. Two great examples for clearance fits are nut and bolt assemblies and piston and cylinder assemblies. If you think about it, you need free motion between these components in the direction allowed by design, of course. If they end up having an interference, the assembly will get locked into itself. Now, the next type of fit, interference fit. This is the exact opposite of clearance fit. Interference fit means you always get a negative gap between your features, so the shaft will always turn out larger than the hull. This requires our tolerance zone for the shaft to be entirely above the tolerance zone for the hull. Interference fits always require force to make the assembly possible. These fits are considered permanent fits due to their nature. Steel dowel pins, for example, are assembled into their mating counterpart using interference fit. In most interference fits, you can make the assembly happen by using force, either push force or impact. In some cases, you are forced to even heat up the part so that it expands, thus making the assembly possible. Now the last type, transition fit. Transition fit is the common ground between the two extremes. With transition fit, there is a possibility to get either a bit of clearance or a bit of interference between the two features. These are usually more precise fits, so the gaps are small. Transition fits are used when you require accurate alignment between your features, and precision is key. Remember, you might require some amount of force to make the assembly happen. Bearings, hubs, and gears can benefit from transition fits. Now, before we get into the more advanced parts of the concept, let me clarify two basic definitions. These two are allowance and clearance. Allowance is the difference between MMC of your hull and shaft. This means allowance is either the minimum clearance between parts in case of clearance fit or the maximum interference between parts when dealing with fits that cause interference. This means allowance is positive for clearance fits and negative for other types. Now the second term, clearance. Clearance can be thought of as the opposite of allowance. Clearance is defined as the maximum intended difference between the two parts, which means the loosest possible fit allowed. Clearance is derived by subtracting LMC of the hull from LMC of the shaft. Clearance is positive for clearance and transition fits, while it becomes negative when dealing with interference fits, which is common sense. I think you got the idea. The basics are easy to grasp, but there is still much more to fits than just the three main types. Okay, so now that we know the three main types of mechanical fits and also some necessary definitions, let's take it up a notch. Each of these fit types have different subcategories based on the tightness of the fit, and they each have their own use. We have different definitions for ISO and ANSI systems, but the principles are the same, give or take. In this video, I'll be focusing on the ISO version of fits. But even if you use the ANSI, I highly recommend you to watch this video. So let's start by looking at this chart here. This is the ISO chart for fits. We have our basic or nominal size for both shaft and hole marked here on the right. This means we use the same nominal size for both shaft and hole and apply different tolerance combinations for each to specify various fit types. Each vertical combination is a unique fit type. Holes have alphanumeric codes with uppercase letters and shafts with lowercase letters. As you can see, we have the largest gap between our shaft and hole tolerance zones on the far left. This gap reduces as we go right on the chart until we go into transition zone and then finally interference zone. The first 5 columns are clearance fits, the next 2 columns are transition fits, and the last 3 are interference fits. Each fit has a name of its own. Starting from the left, we have loose running fit, free running fit, closed running fit, sliding fit, and locational clearance fit. These are all clearance fits. Next, we have similar fit and fixed fit, which are the 2 types of transition fit. These 2 fits are also known as simply locational transition fit, which is just a different name for the same fit. And lastly, we have locational interference fit, medium drive fit, and force fit for our interference fits. Locational interference fit is also known as press fit. Now let me emphasize that different sources might use alternative names that I mentioned for some of these fits, which is completely okay. What's important here is the alphanumeric code combination, which works as an identification code for your fit, so keep that in mind. Also remember, we have 2 concepts of allowance and clearance when dealing with fits. Allowance is the delta of hole's MMC size from shaft's MMC size, which is positive for clearance fits and becomes negative for the other 2 types, and clearance is the delta of hole's LMC size from shaft's LMC size, which is positive for clearance and transition fits and negative for interference fits. Now, let's understand what this all means. If you noticed, all tolerance zones for the holes have uppercase H here. Capital H simply means hole's MMC is aligned on the nominal size. This means the tolerance zone for the hole in every single fit type here will have a unilateral tolerance that has 0 as the lower tolerance limit. If you think about it, this entire table is aligned based on holes, and the shaft tolerance zones move up or down to adjust. This is what we call hole basis system, which is more common to use. An alternative is to use a shaft basis system, which is the exact same thing with a different arrangement. This time, every single shaft has a lowercase h, which means MMC of all shafts are all aligned on the nominal size this time. In this system, the unilateral tolerance with 0 on one side belongs to the shafts, and the holes have to adjust their tolerance zones respectively. Now, as I said earlier, hole basis system is much more common, so that's what I use here. Now, what does each alphanumeric code combination present, and how can we translate them to actual tolerance values? Whenever you look at any of these values, separate the letter from the number. Think of the letter as the deciding factor for where the tolerance zone is located with respect to the nominal size. Now, the number in front of them is the IT grade or tolerance class. You can think of the IT grade as the deciding factor for the scale of tolerance zone. It basically defines how large the tolerance zone is, but not its location. Also remember, both the alphabetic part of this code and the numerical part are calculated based on the nominal size of the features. So a larger shaft or hole will have larger tolerances for the same alphanumeric code as it should. This is really important, so make sure you get it. There are standard tables that are used to derive these values, which I will get to. Now I'd like to go over both parts of this alphanumeric code in more detail because they are very useful and also very interesting. Trust me, you will thank me later. So as I said, the alphabetic part tells us where the tolerance zone is located with respect to the basic or nominal size. Look at this graph here. This is called the fundamental deviations graph. We have one for the shaft and we have one for the hole. These letters start from A and go towards Z with some exceptions here and there. First of all, we don't allow the letters I, L, O, Q, and W because they can be confusing and misread, especially since we have a case-sensitive system here. Another exception is that we have CD between C and D, EF between E and F, and FG between F and G. There is also JS that goes next to J, and also ZA, ZB, and ZC that all go after the letter Z. This gives us 28 different classes for our fundamental deviations. Now, don't let these confuse you more than they should. What is important here is the fundamentals and general understanding of the entire concept. Each letter here is defining the distance between the nominal size and the upper or lower limit of our tolerance zone, whichever one that is closer to the nominal size. So for holes, for example, A tells you where the lower limit of the tolerance zone is with respect to the basic size. The upper limit is specified based on the IT grade that is chosen, which tells us the size of the tolerance zone. We do not care about that at the moment though. Right now we only care about the letters which tell us where the limit closer to the basic size is. As you can see, the distance from the lower limit of our tolerance zones is decreasing from A to G, and it hits 0 when we get to H. The shaft is the same way, but in an opposite manner. With the shaft, the letters A to G tell us where the upper limit for tolerance zone is with respect to the basic size. H defines a 0 distance, just like what we had with the holes. Now, J and K are tolerance zones that can go positive or negative for both shaft and hole. They provide different values based on the IT grade. M and N are also a bit weird when we deal with holes. They provide different values based on the IT grade, just like J and K. Anything after P goes in the opposite direction, moving towards more interference. These ones define the upper limit for holes and the lower limit for shafts due to their nature. Remember, the rule was that these letters tell us about the limit being closer to the basic size, so keep that in mind. There are standard tables in ISO that specify what the fundamental deviation value is based on the basic size of our features, so you don't have to memorize most of the stuff here. These tables tell you exactly how far away you should be from the basic size and on which side of it. As a general rule of thumb, letters A to H are used for clearance fits, letters J to N are used for transition fits mostly, and letters P to ZC are used for interference fits. A couple of things that you should be memorizing though. First one is letter H, which you're familiar with already, but I'll go over it one more time due to its importance. H means a fundamental deviation of 0. This means when you see capital H for holes, our tolerance zone is unilateral, going positive with the lower limit being 0. Similarly, lowercase h used for shaft means a unilateral tolerance going negative from basic size and 0 as its upper limit. Second thing to memorize is fundamental deviation JS. JS is always a symmetry tolerance, which means it goes both positive and negative the same amount from our basic size. Remember, there are in fact equations behind each one of these letters that has your size as a parameter in its calculations, but that is too technical for our needs. All the useful alphanumeric combinations are available in standard tables based on your nominal size, so you don't need any calculations. I think this has been relatively heavy, and I will of course go over an example later in the video so you fully understand it, so don't worry too much right now. Now we get to the numerical part of our alphanumeric code, being our IT grade. IT grade stands for International Tolerance, and it defines the size of our tolerance zone. We have tolerance grades from IT1 to IT18. The lower the number, the finer the tolerance zone. So IT1 provides the tightest value among these ones, and IT18 the loosest tolerances. There are also IT grades of 0, 1, and 0 which come before IT1, meaning they offer even tighter tolerances. ISO 286 provides tables that tell you what the tolerance size for any given IT grade is based on your nominal size. This way, everything is with relation to the size of our feature, which is how it should be. Let me also mention something important about tolerance grades. Every machining process is capable of providing a specific range of IT grades. If you look at this table, you see what I mean. As you can see, lapping and honing provide us with the tightest IT grades, and as you go down the table, you get to less accurate machining methods. Another very important piece of information is this chart here. This chart tells us measuring tools are manufactured using IT grades of 7 or lower, and non-measuring tools, typically called materials, use IT grades of 8 and above. Fits use IT grades of between 5 to 11 based on the fit type and nominal size. Larger manufacturing processes provide IT grades of 12 and above. You get the point. Now let's go over an example and use the standard fit tables to figure out what our tolerance for shaft and hole should be based on our nominal size. Let's say we have a shaft and hole assembly with a basic size of 10 mm. Say we are told to apply the proper tolerances that give us a free running fit. If you look at our fit table, you see that free running fit means H9 for hole and D9 for shaft. 9 for both means they should have equal tolerance zones in terms of size. H9 should be placed with its MMC at basic size and D9 at a distance in the negative direction. Now we should refer to the fit tables from ISO 286 to figure out the tolerances to use. If you look at this table, you see that for free running fit with a size of 10 mm, the hole goes from 10 to 10.036 mm and the shaft goes from 9.924 to 9.96 mm. This is a tolerance of 36 microns for both the hole and the shaft. Now let's calculate the allowance and clearance for this fit. Allowance is the delta of hole's MMC from shaft's MMC. This gives us 40 microns, which means our gap won't go under 40 microns with this fit. Now clearance is the delta of hole's LMC minus shaft's LMC. This gives us 112 microns, which is the maximum size our gap can get. Now as you would imagine, the same fit with a larger basic size instead of the current 10 mm can lead to larger tolerance, allowance, and clearance, which is common sense. Say we have 20 mm of diameter instead of the original 10 mm. This gives us 52 microns for the hole and shaft tolerances this time, which is 44% larger than what we had with a size half of this. Our allowance is also 65 microns now, and our clearance is 169 microns. You get the idea. Now, let's make it a bit more interesting by specifying tolerances from a medium dry fit for the same 10 mm example. This is an interference fit known with the H7-S6 combination. The shaft with an IT grade of 6 must have tighter tolerance than its mating counterpart, being the hole, which uses IT grade of 7. As you can see, the dimension for the hole is 10 mm up to 10.015 mm, and for the shaft we have 10.023 up to 10.032 mm. This is a tolerance of 15 microns for the hole and 9 microns for the shaft. Now let's calculate our allowance and clearance. Allowance is our hole's MMC size minus our shaft's MMC. This gives us negative 32 microns. Clearance is hole's LMC size minus shaft's LMC, which gives us negative 8 microns. This means we will always have an interference anywhere from 8 to 32 microns when our basic size is 10 mm. I think we got the idea. I suggest you to get familiar with fit names and practice them from time to time so the concept stays in your mind. Remember, all you need to do is to use standard fit tables to derive your tolerances based on your fit type and nominal size of your assembly. Now, if you enjoyed the video up to this point, I appreciate it if you could like this video and subscribe to my channel. There is still much more to GD&T which requires studying and practice. For those of you serious learners, I have a full professional course on GD&T that covers all aspects of GD&T with many examples, quizzes, and state-of-the-art graphics that make learning this complicated subject a breeze. So check it out if you're interested. I hope you learned a thing or two from this video today, and I hope to see you again soon. Have a great rest of the day.